So, have you ever stopped to think about how a single computer could handle, say, a public press release and top secret intelligence at the exact same time without any leaks? It sounds almost impossible, right? Well, today, we're diving into Solaris Trusted Extensions, a system designed to do just that. And hey, if you're studying for any OS security exams, you are definitely going to want to stick around, because we're breaking down everything you need to know.
All right, let's just jump right into the core of the problem. Picture this. You're an analyst, you've got a public press release open in one window, and a top secret intelligence brief open in another, all on the same computer at the same time. So the billion-dollar question is, how do you build an operating system that can guarantee with absolute 100% certainty that not a single bit of data from that secret document can ever leak into the public one? That is the fundamental challenge Trusted Extensions was built to solve.
So here's our game plan. We'll start with the MLS security challenge itself. Then we'll get into the key building blocks, labels, and zones. After that, we'll unpack the access control trio, look at how the system replaces the all-powerful super user, and then see it all work in action. We'll wrap up with the key security takeaways you'll want to remember. Okay, first up, the why. To really appreciate what Trusted Extensions does, you have to understand that traditional security measures, passwords and basic file permissions, they're just not going to cut it. That's like putting a simple padlock on a bank vault. When you're dealing with data where a leak could have national security implications, you need something way, way stronger. The solution is a concept called multi-level security, or MLS. And honestly, the easiest way to think about it is like a one-way valve for information. Data can flow up from less sensitive levels to more sensitive levels, but it can never, ever flow back down. It's a one-way street, period. This principle is the absolute bedrock of high-security systems, and it's at the heart of everything we're about to talk about. So, how does Trusted Extensions actually pull this off? How does it enforce that one-way data flow? Well, it all comes down to two brilliant concepts that work together, labels and zones. Let's break them down. The first building block is the security label. And when I say everything gets a label, I mean everything. Every running process, every file on the disk, every packet on the network, each one gets a digital stamp. And this label has two parts. First is the classification, which is the hierarchy you'd expect. Public, secret, top secret. The second part is compartments, which are non-hierarchical categories like need to know. This label is the absolute cornerstone for every single access decision the system makes. So you have all these labels, but how do you enforce them? That's where zones come in. Think of a zone as a perfectly sealed, soundproof room. One room is labeled confidential, another public. Anything happening in the confidential room is completely invisible to the public room, total isolation. And to prevent any kind of cross-contamination, if both rooms need the same tool, the system makes a separate private copy for each. That's a fancy term called polyinstantiation, and it brilliantly prevents a lower-level process from messing with a higher-level one. All right, so we have our building blocks, labels, and zones. Now let's look at the three-part model that actually puts these tools to work and enforces the rules of the road. Now, for any exam, this is a key point. You can remember this model as SRP. Secrecy, roles, and privileges. Secrecy is the main event. That's the core MLS policy based on labels. Roles are all about confinement, reining in what even powerful admin accounts can do. And privileges are the special exceptions, giving a process a very specific, discrete right to bypass one single policy without handing over the keys to the whole kingdom. This brings us to what is frankly one of the most revolutionary things about Trusted Extensions. How it completely rethinks the all-powerful superuser, a concept as old as Unix itself. For decades, the root account has been the holy grail for any attacker. It's the one key that unlocks the entire kingdom. If an attacker gets root access, it's game over. The system is completely, totally compromised. And Trusted Extensions basically says, yeah, that's an unacceptable single point of failure. The first part of the solution is to just shatter the power of root. Instead of one superuser, Solaris breaks its power into more than 68 tiny, fine-grained privileges, and these are managed in 4 distinct sets. For an exam, remember the mnemonic, I permit effective limits. That's for inheritable, permitted, effective, and limit. This lets the system give a process only the exact privilege it needs for only as long as it needs it. The second piece of the puzzle is role-based access control, or RBAC. This is just brilliant. Instead of giving powerful privileges directly to users, you assign them to special accounts called roles, like System Administrator. A regular user can then temporarily assume that role to do a specific job.
It is the perfect enforcement of the principle of least privilege, giving people only the power they need right when they need it.
Okay, that's enough theory. Let's see how all these pieces actually come together in a real-world system. This is where the rubber meets the road. Check this out. This shows the famous read-down policy in practice. Let's say we're inside a confidential zone. We have full read and write access to our own files. But notice, when we look at directories with lower security labels, like /usr or the public home directory, we can only read them. We can look, but we can't touch. Trying to write data from our high-level zone to a lower-level one is strictly forbidden. The system just won't allow it. In this image, this really brings it all home. What you're seeing is a single user on one desktop working with applications at 3 different security levels all at the same time. To the user, it feels totally normal, but behind the scenes, the operating system is watching every single move. You try to copy text from that restricted window and paste it into the public one? Denied. The system will block it instantly because that would be a security leak, and that's the one thing it's designed to prevent. And this intense security doesn't just stop with files and windows. It extends to the whole shebang. Network traffic itself is labeled, so secret data stays in its lane. Printouts are automatically stamped with the correct banners and footers. Even just plugging in a USB drive is a secure, managed process to make sure data isn't moving to the wrong place. All right, we have covered a ton of ground. So let's boil this all down into the key takeaways you're absolutely going to want to remember for any exam question on this topic. If you're writing an essay or tackling a short answer question, these are the 5 points to hit. Number 1, MLS is enforced using labels and zones. That's the foundation. 2, the all-powerful root user is gone, replaced by fine-grained privileges and RBAC. 3, remember the access control trio: secrecy, roles, and privileges. 4, its killer feature is letting one user manage multiple security levels on a single desktop. And 5, this one is subtle but critical, enforcement happens at the zone boundary. This is huge because it means most regular apps can run inside without modification. And that's our deep dive on Solaris Trusted Extensions. It's an incredibly powerful and elegant solution to the problem of multi-level security. But it does leave us with a pretty big question to chew on. If we can achieve this level of near-perfect isolation for secrecy, what's the next great frontier that operating system security needs to conquer?